Welcome back to week 2 of our course Boltzmann Law, Physics to Computing. And this is the 5th and last lecture for this week. Now, in the last lecture, we showed how it would be interesting to have these multiple peaks in your state space response, because you could use that for inference and for a new kind of logic. We also introduced this bipolar representation, where instead of 0 and 1, you use -1 and +1. And we also then described an approximate way of designing your H and J to get a particular desired response with multiple peaks. And that was the recipe we put down is here. As I mentioned, this is an approximate method, so we won't really be discussing it much. What we'll do in this lecture is we'll talk about a much more general method that is widely used. Okay? Now, this method that I had mentioned at the end of the last lecture, that only works when you have very few lines of your truth table. Remember, this table tells you the peaks. Each row corresponds to a particular peak, and those are the rows of your truth table, whereas the number of columns, that's the number of bits that you have. In this case, we assumed it was 6 bits, and we have 6 peaks as well, but those two don't have to be equal. And the point is, when you have many more bits than you have peaks, then this rule often works well. But what we'll be describing to you is something that's a little more general and much more widely used. Now, although the rule will be different, but the thing is these quantities are of great interest in their own right. And that's what I want to stress in this lecture to start with, that these are interesting things and they play an important role in this algorithm that I'm going to describe to you. Okay. So first let's look at what this quantity is. So this Tm is our truth table, of course written in bipolar notation. So instead of zeros and ones, you got -1s and +1s. Now this is Tm transpose times 1, and that's a column vector. But let's look at the transpose of this quantity. So I have to take the transpose of this product, which is like the product of the transposes, but in reverse order. So instead of T transpose 1, I have 1 transpose T. And that's like the transpose of that. So it gives me a row vector. Okay. Now, what is this row vector? Well, the first quantity here, that's this transpose of the 1 vector, which is all components are equal to 1. That's here. And that multiplies this truth table that I had written down. Now when you multiply, what do you get? Well, you are supposed to multiply this row into this column. So effectively what you do is you just add up all the elements here. So it's like these are all the different bits. So you're as if you're going to the first bit, adding up what the value is for all the different peaks and putting it there. Next one, add them all up, put it there. So here it's equal numbers of -1s and +1s, so you get a 0. Here it's 4 +1s and 2 -1s, so you get a +2, and so on. And then you have to divide by this nt, which is the number of rows that you have here, so that at the end of the day, in this case you're dividing by 6, what you're really getting is the average value of each bit. So, in other words, this quantity here is basically the average value of m. Average meaning averaged over all the configurations in your truth table. That's what this is. Or you could write it mathematically in this form. That is, what's the average value? Well, you have to sum over all lines of your truth table. And for each line, you look at this truth table. K tells you which row, that's which line of your truth table you are. And R is the particular bit that you are considering. And then you add them up, all of them, and then you have this multiplication by 1 over nt, which you could view as the probability of getting a particular configuration. Remember, the picture we have is, we have designed it such that you got only 6 peaks of equal probability, so each one has a probability of 1/6, for example. So mathematically, this quantity here can be written this way, right? And you can interpret it as the average value. Now similarly, if you look at that second thing, the one that was the expression for the J matrix, that involves a product of TMs, product of 2 of them. And again, mathematically you could write it this way. What it tells you is the average value of the product of what you have for the rth bit and what you have for the qth bit. So you often call that the correlation matrix, correlation between the rth and qth bits, MR, MQ. And you again do this summation over the truth table. Now, so this is what you get when you have this, have your dream response, the one that has these 6 peaks exactly where you want them. Now, in general, if you just took any network, of course, it would have peaks all over the place. All the different configurations would have some probability. And you could still define an average value, which would look just like this, except that now it's not that there's only 6 lines of your truth table which contribute. It's like every configuration contributes. And so that you have to put in the probability of that configuration, the equilibrium probability, and then sum over all possible, all 2 to the power n configurations. And the same with the correlation matrix. You'd have to sum over all 2 to the power n configurations to get the correct correlation values. Okay. Now, so in general, in a particular problem, the situation is like this. There is a target that you have in mind. You want to get a certain M and a certain MR, MQ. But you don't have it because you don't have the correct weight matrices, the H and J. Instead, what you have is giving you some junk looking like this. And that junk has a corresponding average value and average correlations. So this is what you have, and this is what you'd really like to do. And how do you get from where you are to where you want to be? Well, that's where you have the learning rule. The learning rule tells you that if the target average is bigger than the actual, then you should decrease the H value corresponding to that neuron. It's a decrease, so that means if this, what's inside, if it's positive, then the delta should be negative. That's why the minus sign. And this epsilon is what you call a learning parameter. So you try to keep it small but not too small. Okay. Now, and I'll explain why this works in a minute. But the other rule is, how do I adjust the weight matrices, the weight matrix values? Well, there again you look at the correlations. And if the target is bigger than the actual, then you reduce the corresponding J. So that's the rule, you see. And what you do is, you'd use this learning rule to start from some arbitrary H and J, where you got this mess of a response, and then if you keep iterating, you'll eventually get to your target, where you really want to be, you see. And why does it work? Well, think of it this way. Suppose the target value is bigger than the actual. Then what you really want to do is do something so that the actual increases. So how do you make the actual increase? Well, what I claim is decreasing H will do it. Why? Because you see, H appears in this energy expression. And as you know, what this H decides then is, let's say H is 10. That means when M is plus 1, the energy will be plus 10. When M is minus 1, the energy will be minus 10. So in other words, a positive H kind of puts an energy penalty towards being plus 1. So if I decrease H, what will happen is the energy penalty will get less, and so +1 will become more probable relative to -1s. And so overall, the average value of m will want to increase because there's more +1s than -1s. And that's exactly what we want, you see, because the actual is less than the target. And of course, if the actual are more than the target, then what's in here would be negative, and then you would be increasing the h. Basic point is, of course, this minus sign here. And the same argument goes with the j's. You see, again, if you look at the energy expression, you have the j and the m and this correlation. So if you want to increase the correlation, what you should do is decrease this corresponding j. And I should mention here that the convention we have used, we have written the energy in this form. Often in the physics literature, they define it with a minus sign here. So it is minus HRMR and minus JRQ. And if you do that, of course, this learning rule wouldn't have these minus signs here, just because they would be kind of part of the H and J. But the basic logic is the same. And in the literature, you'll see a lot of, I guess, more rigorous derivations of these learning rules. But what I wanted to show you here is how you can intuitively understand why it works, you see. And then there are details like sometimes people add a term that they call regularization. That is, they don't want this j to increase too much, so they put an energy penalty. So they put a penalty towards being too large, because if it's too large, then you put in a term that will make it want to go down. Okay? Now, how do you actually implement it? Well, again, it means at every step you have to evaluate these quantities and then use it in your learning rule. Now for the target, it's relatively easy. Why? Because I just have to do this summation over my desired peaks. And there's only say 6 of them or 10 of them, maybe 100 of them. But it's much harder to evaluate the actual. You see, in the literature, often the target is called the data, actual is called the model. But the point is, this one, what I actually have, that requires me to do a sum over 2 to the power n terms. And as I've mentioned many times, the 2 to the power n can be a huge number, right? And so, in this context, what you really want to do is not really evaluate this entire sum, but use this time sampling method, the one that works in n space. But you have to take enough samples so that you get an accurate idea of these average values. Okay? And that often can be time consuming. So here's an example of learning a truth table, where the truth table I took as that corresponding to a full adder, which means it has 3 inputs, and then it produces a sum and a carry term. So you have 0, 0, 0, and the output is 0, 0, for example, or 1, 0, 1, and then the sum is 0, but the carry is 1, etc. So the details aren't very important, but this I'm writing in binary notation. So this is a system with 5 bits, A, B, those are the 2 numbers being added, the carry from the last stage, the sum, and the carry out. Okay? And as I said again, the details aren't important. What I want is, I've got 5 bits, so there are 32 possibilities, and I want to have these 8 peaks in my answer. Finally, the 8 peaks correspond to a decimal value of these numbers. That is, if you take these 5 bits and convert it to decimal, you'd get 0 to 31, these numbers. So those are the peaks. So that's what I've shown here. The red ones are the peaks I want. And at first, let's say I've completely disconnected them at first. And so they were all equal height. And then gradually, as you learn, you put in the H and the J, and you gradually, as you can see, the reds are picking up gradually. You see the blues are going down, although 2 of these blues, you'll notice, were still kind of up, but now you can see they're relatively going down. As you go on with time, what will happen is the blues will get suppressed and the reds will pick up. So that's this iterative procedure of how you learn. Okay? Now, before finishing up then, let me say about a few extensions that, as I said, in this course we don't go in detail into machine learning, but I just wanted to mention a few few ideas to indicate the richness of this subject. Like supposing instead of 6 peaks with these 6 bits, we wanted 10 peaks. So then you would actually find that if you just use the straightforward learning method, it may not work too well. And so what often people do is they introduce a set of hidden bits. So these are ones I don't look at. So I still want these 10 peaks, but these 10 peaks correspond to the 6 that I have, and not these other 4 that are hidden that I don't even look at. Now what happens is, again, the learning rule is still the same. But remember, to get the learning rule, of course, I have to evaluate these average values. And now it's a little more harder to do this evaluation because, you see, some of these units could correspond to the hidden bits. And when I tell you the peaks, I'm only telling you the peaks for the visible units. As far as the hidden units are concerned, I don't really care what they are. So I'm not really specifying them at all. And so even when evaluating this, you'd kind of have to do the summation or use time sampling to figure out the correct average values to use in the learning process. Okay? And here's an example that we ran with these, where you had 10 peaks, you had 6 visible units and 4 hidden units. And these 10 peaks I have shown in this kind of two-dimensional plot, where this dimension includes the 6 visible units, so there are 64 possibilities. This dimension has the hidden units, so it has got 16 possibilities. So total is like 16 times 64. That's like 1,024 possibilities, because overall there are 10 units with 2 to the power 10, 1,024 possibilities. And you see, you have got these 10 peaks, but each peak in this visible axis, you see, if you look from the visible side, you got these 10 peaks, but each one is located at a different point in the hidden axis. So, but of course, I hadn't specified anything for the hidden axis. It's not like I told it to have the peak there. It just figured that out on its own, right? So in a way, as if the hidden layer found some patterns in your data that you showed it, this pattern that you showed, and classified them in some way, as if it labeled the data. And this is generally what people refer to as unsupervised learning, that not like someone sat and took the data and labeled it, but it lets it discover the patterns and label it for itself. And another thing you often hear in this field is about generative models. The idea that, well, you show it a few images and train it, but then after that, if you let it run, it will generate new images which will look like what you had and will have patterns in common with it, but these are not things it had seen before. So I'm telling you all this just to give you a rough idea of the richness of this topic. But if you want to explore that, you need to take a real course on machine learning. Here, of course, the main point I wanted to make is just that you can design this bias and weight matrices to give you multiple peaks in your state space response. And these could be very useful for inference and logic. And we just took relatively small toy examples. And one of the problems you have in the field is that when you try to scale it up, the training gets to be difficult. And note that in these Boltzmann machines, they are always undirected. That is, the Wij is equal to Wji, which is why if you wanted to show the connections, point is these would just be lines with no arrows. It goes equally both ways. Whereas the training process is actually easier if you have directed connections, right? And so a lot of the work in this machine learning field is based on directed networks, the ones where you have these arrows showing which ones affect which ones. But all these interactions are one way. If Wij is non-zero, then Wji is equal to 0. And right, as I said, this is where a lot of the action is in the field of machine learning. But what people believe is, in the context of unsupervised learning, generative models, all that, Boltzmann machines could come back and find their niche. But they're used somewhat, but it's just that not as extensively as you might have thought. I just wanted to make that clear. Now, summing up then, as I said, right now we just talked about inference and learning, but in this week we actually started with the sampling method and then went on to show that how X and W, this bias and weight, control the state space response. And then we showed how you could design them to actually solve this constrained optimization problem. And finally, we talked about this inference and logic. And that completes week 2. And what we'll do next week is talk about a third method that we had talked about, the Boltzmann law, and talked about sampling. Now we'll talk about the transition matrix method. That's what we'll talk about next week. See you back. Thank you.